Where exactly are the faults under the Earth's surface? Maybe we can map them using small earthquakes. But, what do we do in regions where there are no earthquakes? And how do we know where faults are in regions that are too deep to have quakes? I wonder if they turn into shear zones.
I just had a eureka moment. If there is a contrast in the dipping foliation, we can find it with harmonic receiver functions. I like to call receiver functions RF now. By using RF we can find the depth of the contrast, and the foliation strike at the contrast.
Microseismicity and receiver function imaging of contrasts, and anisotropy, carry information on subsurface fault and shear zone structure. These can be used to inform the SCEC CFM and CRM. Here is a map showing the new SCEC 5.3 CFM fault model, color-coded by depth. The black dots are the RF locations, and the red boxes show our study regions. Let's zoom in on Parkfield. The San Andreas Fault is delineated by both the CFM and the seismicity. Note, the RF strikes, red bars, parallel this same orientation. On the left side is a map of the CFM fault model, colored points, and the RF locations, black circles. And on the right are these same data in a cross-fault depth profile. We propose that the RFs see slightly shallower dipping ferro-long fabric, but we don't know why their depths dip away from the surface fault. Now, let's zoom into the San Jacinto Fault. This map shows the CFM 5.3 fault model, dots color-coded by depth, and the RF locations, circles, also color-coded by depth. The red bars indicate the RF strikes. We can see that some of the RF strikes parallel the faults, but above the central strand, the RF strikes are slightly rotated. This is a cross-fault depth profile of the CFM 5.3 fault model and the RF converter depths. You can see the RF converters seem to outline a steeply dipping feature. This is a similar plot, but instead of plotting the CFM, here, seismicity is plotted along with the RF converter depths. We find that the seismicity also suggests similar southwest steeply dipping parallel features. The last zoom will be to the Sierra Nevada and Ridgecrest region. These RF arrivals, in the southern Sierra, are from depths close to the Mojo. They cover an area of 50 kilometers across. They are parallel to the Kern Canyon Fault, which activated an old shear zone. We see this sort of distributed, but, fault parallel fabric in many areas. One idea for the Community Rheology Model is to define each shear zone, but we suggest it may be better to define oriented viscosity in blocks instead.